So the circulation of the magnetic field around any closed path, remember for an electric field it was 0, but for the magnetic field it's not 0. It's proportional to the current enclosed in it. So it's a little bit like the divergence, right? So for the electric field we had this divergence law that said that the divergence of the electric field is proportional to the charge contained inside this surface.
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
Lecture 113. In this lecture we're going to use the magnetic force equation that we came up with in the last lecture to derive the Biot-Savart law and Ampere's law. And we'll talk a little bit about the magnetic field in various circumstances, which is actually what we need the Biot-Savart law for. So Biot and Savart had actually come up with this by carefully measuring the force between current-carrying wires. And from their observations, they concluded what is now known as the Biot-Savart law. So let me just show you how we're going to get there. First, let's remember that the magnetic force equation looks something like this. I need some charges here. Test charge, call it source charge, just to distinguish them. V test cross V source cross R hat. These are vectors, and this is all divided by R squared, the separation between them. So this is the force equation that we developed in the last lecture. And in the lecture before that, we had mentioned the Lorentz force law, for which the magnetic portion of it says the force is proportional to the charge times the velocity crossed with the magnetic field, or the magnetic induction field as it's sometimes called, B. I'll probably just call it the B field. So just comparing these two, setting them equal to each other, right, we can see we can immediately get rid of the test charge. I want to solve for B. What is B in this case? Well, the only thing that gets pulled out of here, so to speak, is the test charge and the velocity of the test charge. And that leaves behind this cross product in parentheses, the 1 over r squared dependence, the charge of the source, and of course the constant. So we can write that B is then equal to mu naught over 4 pi. These are just for getting the units right. The source charge, and then we have the velocity of the source charge crossed with the unit vector over r squared. So now what we want to do is we want to turn this into a form which uses current instead of charges. And I want to look at an infinitesimal change in the B field. So I want to look at a little element of charge, right? Because if we have a wire, there's charges moving throughout it, right? And what does that mean? That means it has a current, I, which is just dq dt. Yes? And so what I can do is I can write a kind of dB will equal mu naught over 4 pi. I can replace qs with a dq, so a little charge element, dq. So if we have like a wire, right, and there's a current in that wire, what I'm looking at is a little region, right, of charge right here, you see? And so I just need to manipulate that. Let me just finish writing this out. Cross r over r squared. This dq, though, we can express in terms of I and dt. So we get mu naught over 4 pi. Instead of dq, we're going to write I dt v sub s cross with r hat over r squared. But if you think of the charges, they're moving, right? So if we think of some little charges here, maybe they're positively charged and they're moving with some velocity v, then if we multiply that velocity v times a little infinitesimal time interval, that's the time it takes for charges to go from here to here. So if I call this little length of wire here, I'll call it dl, because that's just the common vernacular. Short length of wire, right? Then dl dt is equal to that velocity, yes? So that means that dl is equal to vs times dt. And we're keeping the directional nature of it here. right? Because it's along a particular path. This doesn't need to be a straight wire. It could be a wiggly wire, in which case we need to keep track of the direction as it goes through, because these are going to end up being path integrals. So I can replace dt times vs with dl. And so we get the final form for the Biot-Savart law in its infinitesimal form anyways. Looks like mu naught over 4 pi I dl cross r divided by r squared. Did I get everything? I think so. And so this is basically the Biot-Savart law. It says that we can calculate the magnetic field at some test point by integrating along a path, right, along the wire, whether it's curvy or straight, crossing it with the direction vector r, which points to the test point we're interested in, and of course it's inversely proportional to that distance squared, how far away the test point is. So that's essentially it. Sometimes you'll see it in integral form, but now let's use it, because this is what allows us to calculate the magnetic field, right? Because magnetic fields are generated by moving charges, and so this is how we do it. So we're going to do it in two circumstances. We're going to calculate the magnetic field around a long straight wire, which is a result we used in the first lecture that we did on this topic, lecture 111, I think it was. And then I think we used it again in 112, but we're going to calculate that result now. It's fairly straightforward. And then we'll also look at a case of a loop of current. So if I had a little current loop, a little ring where charge was just going around constantly. First, I'm going to write this result down over here. R T I I E L R. So first, when we do these kind of problems, we need to very carefully draw the geometry of the problem. Okay, so we're talking about a long straight wire here. So we'll make a long straight wire. This will be our test point, call it P. I could have made it a little more symmetrical, but that's fine. And it will be located at a distance, we'll just call this Y. And we'll call this distance here to some current element. So let me try to utilize these colored markers I've got. That's a little DL, right? That's a little chunk of the wire where the current is that we're talking about. And this will make, of course, well, really this is the R vector here. Okay, I think I have all the labeling that I need on here. I'm going to call this theta 1. We'll consider contributions from the other side of the wire as well. I'm not really going to go into detail on that. Theta 2. But we'll make that argument by symmetry. So we'll do a calculation to calculate the contributions to the magnetic field from the little charge elements all along the wire on the right side, and by symmetry we'll get the left side too. So where do we start? We start with this Biot-Savart law, right? And we write down, okay, dB is going to be mu naught over 4 pi, and we'll have the I dl here cross r over r squared. The first replacement that we can make, right, is this dl cross r, because dl, right, I dl will just be equal to I times dx, where this is the little dx right there, in the I direction, or the I hat direction. So this will give us mu naught over 4 pi. We'll call it I over r squared. And we'll have dx, and then we have I cross r hat. So the I vector points in this direction, the r hat vector points in this direction. You'll remember that the cross product is the magnitude of the first term times the magnitude of the second term times the sine of the angle between them. And the sine of the angle between them is phi, as I've marked here. Since their magnitudes are 1, this is just going to be mu naught over 4 pi I dx over r squared. 1 times 1 times the sine of phi. But we can use a more convenient angle here, because if I look at this angle phi, and I put a little perpendicular right there at that point where dl is, this of course would be 90 degrees, and we know that the sine of phi will be equal to the sine of 90 degrees plus this little bit here. Well, what is this little bit here? Well, if you think about it, And we just draw a temporary triangle here for you. Here's this perpendicular line that makes this angle theta 1 right here. These are terrible lines. Let me try drawing that again. Here is theta 1. The angle between this and this is theta 1, which means the angle between this and this is also theta 1, yes? Which means that this is theta 1. So what we have here is 90 degrees plus theta 1. And of course, the sine of 90 degrees plus some angle theta is just the cosine of theta 1. So we can finally write that this is equal to mu naught over 4 pi I dx over r squared cosine of theta 1. One other relationship we want to use here is that the tangent of theta 1, in this case, tangent of theta 1, well, that's going to be the opposite, which is x, over the adjacent, which is y. And this means that x is equal to y times the tangent of theta. If I take a derivative of this, dx d theta, I get y. There's two ways to write it. We're going to use the secant version. That's equal to the secant squared of theta. I mean theta 1, by the way. Which is just y times 1 over the cosine of theta, theta 1 squared. Well, what is the cosine of theta 1? That would be the adjacent portion, y, over the hypotenuse, which is this r here, right? So this is equal to y times, since the cosine of theta is y over r, this will be r over y. But everything is squared, so that'll be r squared over y squared. This will cancel one of the y's, and so we end up getting r squared over y, which means we can rewrite dx, which we had here, as being equal to r squared over y d theta. So that will give me that db, see that the r squareds will cancel, and to get b, I just need to integrate. I'm going to integrate from 0 to theta 1 of mu naught over 4 pi I over y cosine of theta d theta, which is just equal to mu naught over 4 pi I over y times the integral from 0 to theta 1 cosine theta d theta. Well, if I take a derivative of a function and I get the cosine of theta, what function is that?
The sine.
Yeah, the sine, which means that the integral of the cosine of theta is the sine of theta. And we would evaluate it at theta 1 and 0. And the sine of 0, of course, is 0. So this just gives me mu naught over 4 pi I over y times the sine of theta 1. And that's going from 0 to theta 1. So that's over here. But similarly, so that we'll call this region 1. Okay, that's the field from here. The field from region 2, which is on the left-hand side, so I'll just put a little b sub I down here. B sub 2 is going to be equal to exactly the same thing, but replace theta 1 with theta 2. So this is mu naught over 4 pi I over y sine of theta 2. And so the total field will be the sum of these two. B total will be, yes?
Yeah.
Well, theta 1 and theta 2 is kind of dictated by where the end of the wire is. But what we're really interested in, and what we're going to really use, is let's imagine this wire is really long. It's so long that we can just call it infinite. What does that mean for theta? Well, as this wire becomes infinite and we add all these up, we start at 0 and we work our way out to the very end of the wire, which is out at infinity. That makes theta go to 90 degrees. Sine of 90 degrees is 1. So this term is 1. 1 plus 1 is 2. And so we get in the end that for an infinite, so I'll write over here perhaps, this will be useful to record, B infinite wire will be equal to, well, 2 times this, we'll just get rid of one of the factors of 2 in the denominator, and so we'll get mu naught over 2 pi I over y. And that is essentially what we got in our, that's the result that we used in lecture 111. I think in 111 we probably call y r, the distance from the wire, which is what this is here, you see. So that is the magnetic field for a long straight wire. The next geometry I want to look at is a loop of current. That's a perfect circle of current. So I really want us to imagine that the current loop is flat like this, so the circle is facing this way, right? And we're looking at it kind of side on. I've kind of exaggerated that a little bit so that you can see it really is a current loop. And this will be a loop of radius r. And we're going to start by considering a point right here at the top of the loop. In this case, the current will be coming directly out of the page. And we're going to consider the contributions at some arbitrary point P that makes an angle. We'll call this theta. And this is, of course, at a distance x. And let's just note that I dl is out of the page. So I've drawn it kind of in the plane. It's really, it's coming straight out like this current is, you see? Yes?
Yeah.
So the magnetic field that will result from this will have two components to it. Okay, there's going to be a component of that field, because it's going to look something like this, let's say. dB. And that will be perpendicular to this vector r, this displacement vector.
Yeah.
I could try and draw some little 90-degree brackets like this. But anyways, but there's going to be a component of this which is perpendicular. And I'll write that as dB perpendicular. And there will be a component in this direction. And I'll call that dB in the x direction.
Yeah.
So out of the page, vector perpendicular to that vector is the B field that's generated from that point right there. But remember, we're going to imagine integrating all around this loop. So we're going to go all the way around it. And so that perpendicular component, all it's going to do is basically spin, right? It'll rotate out like this, all the way around back to here again, yes? So that component is going to completely cancel out. So the integral of dB perpendicular is just going to be 0. So we're only going to get a contribution in the x direction. Let's make a note. What is r? So r, the magnitude of it anyways, will be equal to the square root of, well, x squared plus r squared. So I'm really only interested in calculating points along the axis of the loop, right? That's, imagine an axis going straight through the loop along that axis. If we go off axis, it gets much more complicated. I'm not worried about that. Now, the component we are interested in, though, dBx, right? This is just dB. Put this angle theta right here, times the sine of theta. It's just a component of this field, right? Remember, you can take a vector and you can shift it up. So you can see that the sine of theta does correspond to this dBx. But the sine of theta, what is that? Well, we can get that from this triangle here. That's going to be r divided by the square root of x squared plus r squared. Does that make sense? You can get it from this, because this theta and this theta are the same, because dB is perpendicular to r. But now we need to replace dB. Then we're going to get this term here, r x squared plus r squared times the dB, which we get from the Biot-Savart law, which is just going to be mu naught over 4 pi I dl cross r hat over r squared. But r squared is just x squared plus r squared. Also from the geometry here, if we look at the dl cross r hat, right, you can see these are always making an angle of 90 degrees, right? Because like I said, the current loop is coming out of the page like this, right? It's a circle situated like this, okay? So if we look at it from this direction, here's the circle, but we have it oriented like this, yes?
Yeah.
So this is just going to leave us with this dl here. And so this will simplify to mu naught over 4 pi I dl. This times this is just going to give me x squared plus r squared to the 3/2 power. So the only part that we really need to integrate over is around dl. Well, if we integrate around that path, what do we get? If we integrate the distance around a circle of radius r, that's the circumference of that circle, yes? So this is just equal to 2 pi times r, which means that b sub x, 4 pi I, the 2 and the pi will cancel here. We'll get this. We'll get I over x squared plus r squared to the 3/2. And we have an r here. We're missing an r somewhere. We lost an r. Sorry. We needed an r up here. We had it here, and then I just forgot to write it over here. But we get another r from this integral, so it gives us an r squared. And so this would be the electric field, the magnetic field, at a point on this axis going through the center of the current loop at some distance out here, okay? Some distance x. And there's a special case, right, when so at x equals 0, that's at the very center of this loop, right, the magnetic field is just equal to mu naught over 2 I over r. So if I let x equal 0, r squared to the 3/2 power is just r cubed. R squared over r cubed is just 1 over r. And so that is the magnetic field at the center of a current loop. Another place of interest we could look at, however, is at infinity. So if we let x go to infinity, now the r down here doesn't matter so much. And so we're just going to get, oh, well, okay, I'm going to put that pi in here, and I'm going to cancel it out up here, and I'll put an r cubed, r squared, up here. Yeah, so I'm just letting x dominate over r, so the denominator will just be x cubed. I'm putting in a pi here because of the definition. This will be mu naught I over 2 pi, call it m. Well, actually, I'm going to call it mu x cubed, where mu is called the magnetic moment. Actually, I don't need the I either. I can just leave this term like this. I times pi r squared. Now, I'll talk about moments in a moment. But now this kind of makes it an analogy to, if you remember from electrostatics, we had this electric field for a dipole, where P is the dipole moment. That's the charge times the separation distance between the charges, okay? And it took this form like this. That's why I put it in this form here. So for a far distance out, this current loop looks like a magnetic dipole. Now, I didn't integrate around the full geometry here, just along the axis that goes through the center of the circle, the loop of current. But if you were to go around the axis, you would see that it looks like the field for a dipole. So let me just spend a moment talking about these current loops as a magnetic dipole and what the field looks like. As a result, I want to save B loop. I guess we could also write something like this, dipole. These dipoles will turn out to be important. I think I've already stated that, as far as we know, there is no such thing as a magnetic monopole. It's not like charge, right? So magnetic fields always result from moving charges. So how can we have a unit? How can we have a thing we can hold in our hands have a magnetic field? Because charge has to be flowing, right? So the only analogy we can come up with that makes any sense is, say, an infinitely long wire where it's always going, because it has to start somewhere and stop somewhere. But a current loop, right, is a way to do that. If you have a little loop of current, then you've got a magnetic dipole. And so what does that field look like? The loop will get the current loop again will be in the plane. So here's the circle, right? And I'm going to take it and turn it like this and put it right here. And so what we see are magnetic field lines racing straight through as we get closer to the edge. But what do they do after that? Well, as it turns out, magnetic field lines loop back on themselves. And we could, if you wanted to, kind of think of this like north and south. Now, I don't want to spend a lot of time talking about drawing magnetic field lines like we did when we talked about drawing electric field lines. But let me characterize the difference between magnetic field lines and the electric field lines. Make a table here. Feature, and we'll put E for electric field and B for magnetic field. Start and end. Well, recall that electric field lines begin or start on positive charges and they end on negative charges. Whereas magnetic field lines are always closed loops. Okay? So they don't begin or end anywhere. They're continuous loops. What about the divergence? Well, remember that the divergence, right, this is this bit from vector calculus, del dot E is equal to rho over epsilon naught. So you only get flux lines coming out of, you take a volume, an arbitrary surface, put it around a point. If there's a charge at that point, right, inside of that surface, then you'll get a divergence. That means you get field lines emanating from it. Otherwise, the same amount of field lines that enter the surface will be those that leave the surface, and so you get no divergence. Well, what do you think happens? And we're not going to derive this. We could use Gauss's law and derive this, but I don't know how much we're going to talk about flux in terms of magnetic fields. There is a magnetic flux. I just don't know that it's going to be worth our time to go into it. But if you just think about the fact that field lines are always closed loops, what does that mean? Just intuitively, it means that del dot B is equal to 0. And this is actually another one of Maxwell's equations. So we've already seen this one when we talked about Gauss's law for electric fields. And now I'm just kind of throwing that one at you, but it's the same idea. It's just coming from the fact that the field lines are always closed loops. And so there can be no divergence. Yes? Because there are no magnetic monopoles that can act as a source of magnetic field. So there's that. What else do we want to say about this? The source. What is the source of these fields? Well, for electric field, it's charges. Yes? For the magnetic field, it's moving charges, which you could call currents. The geometry. For the electric field, it's often radial or linear. So for example, between the plates of a capacitor, we've got positive charges and negative charges over here. The field lines will be lines just going straight across the capacitor plates. But for magnetic fields, it's usually circular or looped. Finally, axon. What does the magnetic field, what does the electric field act on? Charged particles. And what does the magnetic field act on? Moving charges. I do want to make, I made a mistake here on source. Charges, yes. Really, I want to say the source for this is currents plus one other. Now, the one other I'm not going to get to yet. We have to talk about induction before we can talk about that. But there is another source for magnetic field lines other than current, but we haven't developed that yet, and we'll get to that soon. So this is just a table of qualities about the differences and similarities between the electric field and the magnetic fields, field lines rather. All right, while we're talking about Biot-Savart though, I want to talk about something that's interesting, I think. Imagine that I had a little current element, call this I1 DL1, and it's oriented like this. And I have another current element, call it I2 DL2, which is going this way, yes? The magnetic field felt by this little current element would be kind of out of the page. I'm not sure how to draw it, but do it like this, right? B. It's out of the page. And so the force, with that coming out of the page, will be in this direction to the left. This is the force, we'll say, on 1 from 2. Okay? Now, you remember Newton's third law. For every force, there's equal and opposite kind of reaction force, right? So, by Newton's third law, it should stand that the force on I2 from the magnetic field generated by this I1 should be the same, but equal and opposite, right? So you're going to the right, yeah?
Yeah.
But it's not, because what is the magnetic field from this current loop? Well, look at the direction the current is going, right? The magnetic field, so imagine a wire, right? We can see why this is there, because we imagine the magnetic field. You remember this here's the wire, and you kind of get this. The B field is always perpendicular to that, right? And so you can see where it is here. But here, the magnetic field is 0. The magnetic field from this little current element at this point here is 0. So there's no force at all. And so that would be in violation of Newton's third law, which is weird, right?
Yeah.
Of course, you might then say, well, but you can't really have standalone current elements just sitting out in space like that, right? They have to be part of a larger circuit. And so I could, complete this circuit and say, oh, yes, here we go. Here's this circuit, and then this one would look something like this, I suppose, right? And if we were to then consider, we'd integrate around that entire path and calculate what the magnetic fields were contributing to each of these current loops, and we'd find in this case, now everything works out. It all balances out, okay? But on the other hand, one way we could think of making a little current loop, a little infinitesimal current element like that, right? Without just saying it's part of a larger circuit. And that, by the way, the problem I just put up there, it's a little bit beyond what we can do in this class. It's more of an intermediate level calculation. But that's why I didn't do it. But I just mentioned what the result would be. You would find that Newton's third law does hold for these two circuits. But a way that we could think of making a little infinitesimal current like this would be to just take a charge and accelerate it briefly. Does that make sense?
Yeah.
So it's stationary, then it moves for a second, and then it stops. And then the same thing with this one. So we accelerate one this way briefly and one this way briefly, but at the same time. And it turns out that in the process of that you would see a force on this one to the left. But there's more to the story, because it'll turn out that accelerating charges generate radiation. And so you'll have a radiation, a photon that is emitted, whose momentum will be going to the right, so that momentum will be conserved. So just thought it was interesting to note. We're not going to get into too much detail on that stuff, but let's see. We did Biot Savart. So the last thing I want to hit is Ampere's law. So first recall that an electric field, well, let's say we have an electric field this way. It's a uniform field. And I take a little test particle, some plus Q, and I move it around a path like this. And then I come right back to where I started from. If I come back to where I started from, have I done any work?
No.
You got the answer right. And so as a consequence of that, you can say the potential around a closed path integral of the electric field, some dr over some path, right, is in fact 0. A simple example of that is, you can imagine you've got an electric field and you've got a charged particle, and so as let's say the field line is going this way, and I have a positive test charge. As I move it closer, right, it's pushing back on me. So I feel a force pushing in the opposite direction. I have to do work to get it there. But then when I get to my point, I want to go back where I started from, the field will now do the work to get me back. So the net result is I've done no work, because I got kind of negative work done for me, you see?
Yeah.
I don't know how much detail I want to go into on this, but so the statement that E dot dr, closed path integral, is equal to 0 is almost another Maxwell equation. This is not usually how you'll see it. People will use something called Stokes' theorem, which comes from vector calculus. So if I have a line integral over some closed path and some vector field, that not a scalar field, it has to be a vector field, dotted with dr, this can be shown to be equal to a surface integral. That's an integral over a surface. I'm not going to draw a surface, that's too complicated. Del cross f dot dA. This is some little area element of it. Using that result, we can show that as a consequence of this, that del cross E is equal to 0. And that too is almost another Maxwell equation. Okay, this is valid for electrostatics, but there is a case, which we'll get to soon when we talk about induction again, in which there is a contribution to this. And this is usually called the curl around the field. And you can see that in this case there is none. But soon we'll see where this can be non-zero. And this has to do with changing magnetic fields. That's for electric fields. But now let's think about it for a magnetic field. Is this necessarily going to be true for a magnetic field? Let's see if I can draw. Here's my little wire. I'll have my current going in this direction. At every point around, right, so again, this is a wire like my arm, and I'm making a circular path that is a uniform distance from the wire all the way around. So a circle with the wire at the center of that circle. Okay, and this is the circular path I'm thinking about. And we know from our previous results that the magnetic field is a constant, and it's always tangential to this circular path. The magnetic field for a long straight wire we get from right here. So let's see if we do this line integral, or this path integral, of B dot dr, what's that going to look like? We'll get the mu naught over 4 pi, 2 pi I over y. Let's call this distance here the y. The direction is always tangent, so I'm going to write that as just a little theta as we move an angle around, okay, going from 0 all the way to 2 pi. I'm just going to call it theta hat to mean that tangential direction. And then, of course, we have the dot dr. But if we think about a dr, right, that's just an arc length. So you guys probably remember the formula S equals r theta for the arc length of a chord. If we integrate ds d theta, we can show that this dr, which is you could also call S, dr is equal to, in this case, we're calling it y d theta. And its direction will, of course, be tangential because it is this path tracing out the circumference of that circle, right? So if I replace that in here, this line integral B dot dr is going to look like, we'll get the mu naught I over 2 pi y. We'll pull a y out here. You see that those will cancel, right? We'll get a theta hat dot theta hat d theta. So the y's will cancel. Theta hat dot theta hat, well, those, anytime you have two vectors that are exactly the same direction, right, their dot product is just 1. So that becomes 1. And the path integral around d theta, we just go from 0 to 2 pi. So it's 2 pi. So this integral just evaluates to 2 pi. And so we end up with, and that 2 pi will cancel this 2 pi. And so we end up with mu naught times I. The y's cancel, the 2 pi's cancel, that's it. This is Ampere's law. So I'd like to state, let's write it right here. Ampere's law. So it just says that the circulation of the magnetic field around any closed loop is proportional to the current enclosed in it. So the circulation of the magnetic field around any closed path, remember for an electric field it was 0, but for the magnetic field it's not 0. It's proportional to the current enclosed in it. So it's a little bit like the divergence, right? So for the electric field we had this divergence law that said that the divergence of the electric field is proportional to the charge contained inside this surface that we see the divergence coming through, you see? And then here we have this law, which Ampere's law, which says that the circulation, right, around any loop in space, if there's a current going through that loop, then the circulation around that closed path is equal to proportional to the current contained within it. Now this can be restated using Stokes' theorem as well. Typically what we want to do is instead of writing it in terms of I, we want to write it in terms of J. That's a current density. So you can think of J times an area as being equal to the current. But all right, via Stokes' theorem, we can write that del cross B is equal to mu naught J. And this is almost a Maxwell equation. There's another contribution that's missing, and that has to do with induction, and we'll get to that soon enough. So we almost have all of Maxwell's equations, right? We've got two. The divergence of the electric field is equal to the charge contained within, and the divergence of the magnetic field is always 0. And then we almost have these two curl laws, del cross E and del cross B. There's just a little bit that's missing, and we'll get to it soon enough. I guess the last thing I want to say about Ampere's law is that this is actually how we define current. So the current, the amp is defined, the unit of current is defined in terms of two infinitely long straight wires carrying 1 amp of current apiece and separated by 1 meter's distance will generate a force between them of 2 times 10 to the minus 7 newtons per unit length. So per unit of distance, right? And that's how we define current.
Okay.
Right? Yeah, so what have we done in this lecture? We've calculated, we've kind of derived the Biot-Savart law, at least the infinitesimal version of it, and used it to calculate the magnetic fields for a long straight wire and for a current loop. The long straight wire, the result from that we used to derive Ampere's law, which is going to eventually become one of Maxwell's equations. There's just one little contribution we need to add to it before it's complete. The current loops we're going to use next time to talk about, well, where does magnetism and matter come from? Because I know everyone knows that there are bar magnets and things like that. And so you're probably going, where's the moving charges? And these current loops are going to give us a way to explain the magnetism in matter. And so that we'll talk about next time. Did I miss anything? I don't think so. And we talked briefly about magnetic field lines, but I'm not going to really go into much detail on it. It's very similar in appearance to electric field lines, except that they're always closed loops. They don't begin or end anywhere. And that's because of the lack of existence of magnetic monopoles. And that's all I got for you. See you next time.